The materials science and engineering department at NUS has almost doubled in size from roughly 18 academic staff about 4 years ago to almost 40 today. And we are planning to hire at least another 10 academic staff to the department. NUS has recognized that materials are going to be very important in the near future, both from a purely academic point of view, but also from a societal impact point of view. Many new device concepts and industries require huge advances in materials, and this is a great opportunity for groundbreaking discoveries, spin-offs, and industry impact for the university. The most notable hire for our department was Professor Konstantin Novoselov, the Nobel laureate who discovered graphene, one of the most important material breakthroughs over the last decades, in an institute which Professor Novoselov is heading, the Institute for Functional Intelligent Materials. Other areas of focus for my department are sustainability, soft robotics, and variable electronics.
Some time ago, we started our work with the two-dimensional material graphene, but in fact the whole family of two-dimensional crystals, which allowed us to create materials on demand by sandwiching individual crystals into a three-dimensional van der Waals heterostructures. And then we realized that we create very interesting states with multiple phase transitions. So you basically see live materials which are very reactive and very responsive to the external environment. Smart membranes which can actively monitor the conditions of the water stream, for example, of the surrounding environment. And we try to work on the neuromorphic computers, creating new memorist devices capable of doing those machine learning functions with low energy consumption. We work on the ionic devices, those which can be served as the biotic-abiotic interfaces for healthcare application.
NUS Applied Materials Advanced Materials Corporate Lab, the TICO Direct, was established in 2018 with a mission to develop new materials and complex material solution. The aims of the corporate lab are to build capabilities for the next generation semiconductor manufacturing, not only in Singapore but globally. We also aim to develop industry-aligned talent, as well as to generate startup companies that are based on the work in the corporate lab.
I work on the interface between nanoscience, materials, and electronics to power next-generation devices that involves the use of artificial intelligence. In short, I make AI smarter through material science and engineering. We work on intelligent materials that can sense their environment very well. We hope we can give these materials the sense of a doctor's touch, so that they can allow anybody to immediately have a gauge of how healthy they are through our materials and technology. One of the areas that we are developing is self-repairable or self-healable materials. These materials, they are soft, they can behave like skin. Importantly, they can self-repair just like humans can. By having these technologies involved in the making and processing of materials and devices for electronics, they can allow next generation devices that can heal themselves, even if they are damaged.
So we're interested in how electrons in such systems interact with terahertz and infrared radiation, which is important for many applications. So for example, we can apply this technology for quantum communications, we can look into gas sensing, we can look for beyond 5G communications, navigation of autonomous vehicles, and many more other directions.
My research mostly focuses on quantum technologies. In particular, my main project is about linking the information carried by telecom photons, the kind of photons that carry information in the telecommunication network, together with superconducting qubits, which are a nice building block for quantum processors.
For many years, my group has been working with industry closely. One of them in Singapore is ST Engineering on different types of new batteries. Lithium-cell batteries can offer much higher energy density in principle. They can also be made at much lower cost. So we are in the process to make the lithium-cell battery to be able to recycle for a long time. So this will be a big breakthrough for the technology.
Our lab has been quite extensively working on the new research platform we call the electrified chemistry to address the critical issues confronted by our society, from energy and to environmental issues. So there's quite a number of the the applications we can use based on the electrified chemistry, from the high energy density, the flow battery for stationary energy storage, and to the on-demand hydrogen production, and also to, we call this the electrometallurgical battery material recycling. It's mainly for the waste lithium battery materials. And in our lab, we have been quite closely working with the industry, by licensing our technology, and also we have the very excellent young people, so they have the idea to have a spin-off to commercialize the technology.
My vision for the department is that it becomes the globally leading department in material science and engineering. That it provides the best possible education for our students, and that it is a place which nurtures talent on all levels. I also would like to see that our department becomes the go-to place for industry whenever they run into fundamental problems with their processes related to materials or new materials to enable their revolutionary new device concepts.